Okay, so I'll come back to my lecture. So we I'm going to go back into this Heitmann-Radon type energy now. So remember we have the set of configurations. So I'm not sure we show again the notes from this morning. So we now look at the 2D Heitmann-Radon model. So we have endpoints in the plane, and the energy is this one here. So some of the pair interactions of this particular interaction potential V, which is the limit as p goes to infinity of the P2P Lennard-Jones, which is plus infinity for this is less than 1, minus 1 at r equals 1, and 0 at r bigger than 1. But in fact, we are also interested in the P2P, and the first thing that I will okay, but we are also interested here in the soft one, in the Lennard-Jones one, which is actually the more physical one, because at the end of the day, when we want to see things like elastic energy contributions, we need really the soft one. So actually, what I will do now with the energy decomposition, I want to talk the whole hour about the soft potential here. Okay, so and then tomorrow we're going to go back. So basically the headline is so, and it's also the energy decomposition for soft potential. So I mean, finding the ground state works rigorously in this limit, but the energy decomposition is rigorous for soft potential. So we are very, very proud of that. So it works for real. Okay, and so we already introduced the bond graph. So that was a pretty boring thing. So we just fix a sort of range. Maybe I draw a picture. So for the soft potential. So I think I didn't do a good job at drawing a picture. So here's one. So the optimal. So the depth of the potential where it was normalized to -1. You can always do that for this attractive repulsive potentials. So here's my potential V, and then we fix some range on here where we consider the thing bonded. So it's something like when the energy is sort of in this range here. So that's really where the bond sits. So that's an alpha and this is a beta. And whenever the interparticle distance sort of x minus y is in this red range, then we call the thing a bond. And then that contribution will then be split into a combinatorial -1 and an elastic contribution, which is the deviation from the combinatorial -1. Okay, and the main work is to work on the combinatorial -1s. So yeah, so that's that. So let me put this thing away now and really get into what more do I do with the decomposition. So the combinatorial contribution. So this was when we take this bonded term. Maybe I should leave it here for good. Okay. Like so, is that better from the sound? I think that would be better. Okay, yeah. So the combinatorial energy contribution would be the -1s. So it's really minus the number of edges. it's -1 for each edge. And so that will be the first part to try and decompose. So I wanna start with that. So it turns out, so we thought for a long time one can work directly on the bond graph, but it's not very good to work with a bond graph. So what topology is built by triangulating manifolds. So you have to work with nice triangulations, because only then you have like nice cohomology theory or simplicial complexes and things like this. So we have to triangulate, and so here's how this goes. So I start with the so before we start, so we do so the edge set was the bonds. So E was basically xy and x cross x. So x minus y in the interval alpha beta. But then we do an enlarged, so this was the edge set, but now we do an enlarged edge set. So E bar is basically E union some additional edges. And so what are these additional edges such that all faces are triangles? Okay, so I forgot to define faces, so maybe I should define faces. So the original faces are defined as follows. So faces are the following. So we really use the embedding into R2. So if I draw, I mean, like for example, let's do something like this. Some configuration which looks like this. Okay, so and there could be some other stuff sitting here. Okay, and so what is a face? So I really use the embedding and say it's really the open connected bounded subsets of R2. Such that so we can say that the boundary so the boundary is given by a cycle. So I equals 1 to k of the set xi. So xi minus 1 xi. For some points x0, xk equals x0 in x, where xi minus 1 xi is always an edge. Okay, so this way we get the faces. So the faces have to be bounded by a cycle. So for example, this that's a pen here. Shape things with pencils. So in particular, so there's some people. So how you define faces in graph theory? I mean, it's of course up to you. Depends on which graph you want to obtain. So for example, this thing here would be a perfectly fine face. But if I have only 5 edges here of length approximately 1, if my bond interval is close to 1, I will not be able to fit another particle, so it would look like that. Okay, so that's a perfectly fine face. with this definition, a face needs to be bounded by one cycle. So sometimes in the literature, you find people who believe like rings should be cycles. So so let me draw a non-face. So for us, so if you do something like this, I just draw it very roughly. So something like this is not a face. Okay. So ring, according to this definition, is not a face. So face has to be bounded by a cycle. Okay. However, since we're interested in general configurations, that's actually one of the things I love about the title and announcement of the school, that it's about point configurations and not just nice configurations. It's general configurations. So it could, for example, look like this. So I could, if I have 7, let's so for example, here's a guy with 7, and then I could stick one wire, so to speak, here. So that's a perfectly fine face. So I didn't say in this definition that the xi's needs to be pairwise disjoint. I just need to say the first guy is equal to the last guy. So basically, if you kind of run along, so if you run along this guy, sort of, so you have this edge twice with different orientation from here to here, and then back here. So that's a perfect cycle. So the edge is a perfect cycle.
And it's a face.
Sorry?
And this is
sorry,
a
a perfect face. It's a perfect face. And so this is a cycle. So so that's the definition of the face. And so then we add now additional edges to make the faces into triangles. So so these additional edges. So how I triangulate, it doesn't usually matter for what I do last. So this would be typical additional edges here. Okay. So whenever I have a face which is not a triangle, I can triangulate. And so then I need to introduce an error. So basically, it's a natural way of counting. So I introduce a thing called mu of x, which is basically the number of points in E bar minus number of points in E. So it's a non-negative number, it's non-negative integer, and we call this, it's a defect measure. So and so it turns out, so this is independent of the way I triangulate. So independent of choice of triangulation, only depends on E. So this defect measure, even though in the definition it has the E bar, it doesn't depend on the E bar. If I triangulate in some other way, I get the same number of triangles. Yeah, so that's a unique number of triangles to which I can split given face by additional edges. Okay. So then that's a first nice contribution. And so then on the E bar, I can do a much nicer geometry. So I can. I also want to talk about the second quantity that we're going to need is so we define So the next thing we need to do is talk about the different types of edges. So edges, so you have 4 types of different edges. So there is a regular interior edge. So it lies on boundary of 2 faces. So some guy like this here would be fine as a regular interior edge. Then we have a regular boundary edge. So it lies on the boundary of 1 face and on complement of all faces. So the outer region is the complement of all faces. So this would be like a regular boundary edge. So for example, this guy here is just a regular boundary edge. It lies on the so it lies only on 1 face and on the boundary also on the complement of the union of all faces. So, but there are 2 other kinds of edges. So there is these things we call wire edges. So they're only like so let's call it outer. So it's an outer wire edge. So so the outer wire edge is not on boundary of any face. So that would be, for example, this this guy here. So this lies not on the boundary of any face. It's just like hair sticking out. And then the last thing that can happen is that there could be a wire edge, but it lies inside the face. So these are the only possibilities of edges. So so inner wire edge, so that would be this guy here. So it's on boundary of precisely of 1 face, but not on the boundary of the complement of all faces. Yeah, so these are the 4 possibilities. And so then we can also, once we have classified some of the edges, we can classify the particles. So when you do crystallization stuff in R2, it's important to know whether your particle is a boundary or not. So so we have something like so let's say so particles we also have interior. So if incident only with interior edges and boundary, it could also be a particle like this. I think my configuration doesn't have to be connected. So boundary particle would be incident with no edge or edge. Okay, and so this would be give me a set int x, and this is set sort of delta x. Okay, and so now the next thing one needs to sort out. So what's important for these configurations? The contribution to the energy is the perimeter. So how many boundary particles you have, because the boundary particles are somehow missing neighbors. So that will give you a basic contribution. And so, oh yeah, please.
Can you so on that paper, but like a little bit about what we can see. Yeah. So okay, that thing the configuration you have it's not a face with the X through it.
So you mean this one here?
Yeah. No, just
oh, that one
with the X through it. I can't tell if you're pointing.
You have to monitor yourself.
It's the circle inside the circle.
Okay, yeah, this one, it's not a face. So
it's not a face, but could there? So there was something like that. What were those edges? What classification would those edges have?
So they would all be regular boundary edges because they all okay. Sorry, no, they would be wire edges because they are not on the boundary of any face. So then it's an outer wire edge.
Okay.
So that edge is an outer wire edge.
So you don't have to be touching like the outer boundary.
No. I mean, so it's simply when the complement is defined of the union of all faces, not any complement of union of edges. Right? So that so the reason why that turns out to be useful is because I mean I'm not okay. So it sounds a bit like theology because I'm defining it that way, but it's actually not. So the reason why it's a wise idea to do it like this is because then when you add additional edges, you don't change certain things like the Euler characteristic of the configuration. Yeah. So this is a more robust definition under inserting edges, because when you put an extra edge, you increase the number of edges by one and number of faces by one. So yeah, and so it has sort of nicer properties. Okay, so here we go. So these guys are all wire edges. So now, what's interesting about wire edges? So now let's, yeah, okay.
So sorry to completely understand, because the inner circle would be a boundary of the face, right? Because the interior.
Okay, yes,
So that would be a back boundary.
okay, the inner circle, yeah, but I thought we were talking about this guy here.
Oh, sorry, just
sorry, yeah, so absolutely right. So the inner guy, but I mean, I shaded it to say that this thing is not a face, but if I also shade the inner thing, you don't see what I mean. Okay, so the inner thing would be a face, but this ring, the region, I mean, this ring is not a face. So it's just so of course. Yeah, here we go. So then, now what happens with wire edges? So if you have read the book by Herbert Federer on geometric measure theory, so you know how to define the perimeter of stuff like this. And so there is a definition. So an important analysis, important part of the analysis is the length of the boundary. So the perimeter. So the P of X is the following. It's the number of regular boundary edges in E and plus. There is a multiplicity here, so that's the non-trivial thing. So so for the outer wire edges in E, so you need to count these twice when computing the perimeter. And so let me explain this. So that's the definition we know from geometric measure theory. So let me do the following example that will explain it. So this thing here. So we will have so then the perimeter. If you define it geometrically as the inf of the length of smooth curves, so that's how Federer gets to the right definition in this wonderful book on geometric measure theory. So if you take the inf of the length of smooth curves and the edges have length 1, so this definition is the correct one. Okay, so if basically the edge lengths, yeah, so if edge lengths are equal 1, this is equal to the inf over lengths of smooth curves around so X union edges union faces. Okay, so if I take the set of faces, edges, and points, and I take a smooth curve around this and take the inf of the length, I have to count these outer wire edges twice. And so this little combinatorics, so it's like see the books on geometric measure theory. Right, but I mean they're interested there in even more irregular stuff. So for instance, the classic book by Federer, so he explains how to define length of non-smooth sets. and so now if you define it this way, so it has nice properties. So it's also, when you define it this way, let's say so now we have this kind of combinatorial perimeter which assumes the edge lengths are 1, but it matters the size of the mark. And so now I get so to move on, I now need to go to curvature, and so now it gets even more interesting. So now let's do curvature. So I want to now endow this triangular configuration with the notion of curvature. So so what do we do for the curvature? So what do we want? So I want that this is well defined for general and also quite irregular configurations. So I can do nothing about these wire edges that show up here. Yeah, so they can show up. You can have a particle that is just like dangling from some configuration. I have to account for that. And now the second thing I would like to for lattices, I want a reference lattice. So that's, if you want the another one to defining curvature in continuous geometry. So usually you need to take a reference space that tells you what means zero curvature. So whatever curvature you do, so there are different curvatures in the continuum. I mean, there's Gauss curvature, Riemann curvature, Ricci curvature, scalar curvature, all sorts of other extrinsic curvatures. But one thing they have in common, the reference is always Euclidean space. Yeah, so curvature is zero of Euclidean space, and so here in the discrete case, the reference is more complicated because you have so the analogon in the discrete case of the Euclidean RD, which is the real number span of linearly independent vectors, would be the integer span of linearly independent vectors, otherwise known as Bravais lattices. Okay, so the analogon is the lattices, but if you define a notion of curvature which is zero for all lattices, I come to that in a minute. You can do that actually. It was done by a famous guy called Mikhail Voronov. I tell you his definition in a minute. So, but that's not what we want. So, because we want that when we deviate from a reference lattice, that should count as curvature. Okay. So for lattices, so we want basically zero curvature. Curvature is zero if and only if energy, so minimizing, so whatever it is, or otherwise known a reference lattice. So curvature is not, there's no such thing as absolute curvature, there's only curvature relative to a reference. And so here we need to fix one lattice in the discrete world as a reference. Okay. And so at least in 2 dimensions, it's pretty clear what is the lattice. So we just saw in Doug Harden's talk that whatever your nice defects were, and I mean some sort of funny things happening at the edges, but more or less the thing you showed was close to the triangular lattice, to the edge. So that's the canonical. So here we go, and the third thing we want that I want that non-topological defects like elastic deformation. So I really want a sort of topological curvature here. So elastic deformation is something extra. It's not a defect. So no physicist would call elastic deformation a defect. Or also like flat boundaries should not contribute to total curvature. So they may have locally some curvature, but when you integrate up, it should be gone. Okay, so So if you do a little elastic deformation or flat boundary, it should have no curvature. And so then, so there is, so it's basically, so the Gromov notion is quite nice. So should I tell you Gromov's notion? So K Gromov of X. So Gromov's notion is basically the following. So it's basically, so Gromov says you take 1 minus a half times the h degree of x plus the sum over all y in the unit sphere around x. So unit sphere is the one is that are connected by one edge to x. Okay, and then he takes something crazy because this is almost the ones over the face degree of y. So that's a kind of funny curvature by Gromov. So that's a kind of exercise. If you have nothing else to do this evening, you can check that is 0 on like the triangular, the square, and the honeycomb lattice. So if I ask the problem differently, figure out some notion that some function that vanishes from all these lattices, you have to take this one. But it's not good for what? Good for us. So Gromov is out because it violates 2. So let's go back to older guys. So Euler curvature. So that's a pretty nice curvature. I normalized Euler. I didn't normalize Gromov because I didn't want to use my, but I normalized Euler. So Euler takes something similar. So it's 1 minus a half times the h degree of x plus 1/3 times the face degree of x. Okay, so and that is so the half times the edge minus the half the edge degree plus a third the face degree. So so if we have now a regular graph, so we're in a sort of triangular graph. So that means all faces are triangles. So when the faces are triangles, so then you can see that the so the edge degree and the face degree have to be the same. So so if you submit some if you sit at some point here, so that's the x. So then the edge degree, so the number of edges is the same as the number of faces adjacent to that point. Yeah. So when the faces are all triangles, so that's going to be the same. So you can work out what is a half minus a third is 1/6. So this gives you something very nice. So it's 6 minus and I want to write it even differently. So it's the number of edges in the unit sphere of x. So it's 1 of x is all the y in x. Without x, y connected to x by right? And so I can basically view it as an area of the sphere around. That turns out to be useful to look at it this way. So that's the Euler curvature, and so that's a very good notion because it starts telling me stuff about lattices. So for example, here in this case, I get +1 because so the 6 should be really viewed as yeah. So I don't like Euler's definition so much. I think I want to work on the 6. So the 6 is basically the number of edges in the S12. So that's the unit sphere of a point in the A2 lattice. So basically the number 6 here, it normalizes. So it's basically the number of edges in a reference sphere. So A2 is the triangle. Okay, and so then that's already pretty nice. So the only problem is, so for example, if I now have a hexagonal configuration, so in this case we do get curvature 0. And that's not an accident. So in Euler, it seems to come out like an accident, but Euler cheated because he looked for. I mean, he had this in mind. We didn't make it so explicit. So this is like really curvature 0.
I'm sorry, these are like maybe it looks like a good question. Basically, when you have that criteria 1, 2, and 3, these ones they don't talk about the triangular lattice, right? And now we produce the triangular lattice.
Well, I mean, no, I do talk about this because in property 2 for lattices we want that the curvature is 0 for a reference lattice.
Okay,
so it's the relative. So curvature is relative curvature to the reference. So that's what I was trying to explain. Just
so
like in
the composition of the energy, in a way, is well fitted for the triangular lattices, and then maybe
absolutely. So if you want this, this approach only works relative to a reference lattice. So it would be good, for example, in Doug Harden's lovely simulations that he showed me in private and it showed to you in public yesterday. So I mean, when a lot of faces are triangular, but there's some minority stuff that is then it makes sense to work with this. But you know, there's nothing I can do. So differential geometers in the continuum, they do the same thing. So they define Ricci flat means close to Euclidean space. So I mean, you need a reference. I don't think there's any notion of absolute curvature. Curvature is relative. Okay, so yeah, but it's an important point. So it's good that you keep asking about this. So so then there is an Euler with boundary correction. So what I don't like about Euler is now the so it still has a problem with 3. So it's basically so here's the problem. I draw some maybe configuration. What I draw. So if I take this point here, which is kind of like a so I look at the length of the sphere here. So that's so this would have a pretty high Euler curvature that doesn't bother me, but what really bothers me is this point here. So so this point bothers me immensely. So this is sitting on a flat boundary, but I wouldn't say there's any topological defect sitting here. So on a flat boundary, it's kind of unfair to compare to the length of the whole sphere, but it's good to incorporate some of the curvature into a boundary curvature. That's the same what happens in theorems in differential geometry, that you get contributions from boundaries, from manifolds of boundary. And so here, for a point on a flat boundary, it's better to compare to the half sphere. So that's kind of a fair comparison. So what I really take is the Euler with boundary correction. So and the correction is called the discrete Riese curvature. And it was introduced in a nice paper by Oliver Knill from Harvard. So I give some references. I think slides tomorrow. So we almost take the Euler curvature, but so we take k of x is so we take the S1 in A2, the number of edges minus S1 of X. So it's basically 6 minus S1 of X, and X is in the interior, and so only compare with the half sphere minus S1 of X. So it's basically 3 minus S1 of X, when X is a boundary part. And so then that has the nice effect that then this point, like here, it has K of X equals 0. Oh, so it's, yeah, so then this point really has K of X equals 0 on the boundary. Okay, and this corner point, it actually still has, so this would be K of X equals 1 here, but that's fine, that's somehow a special point, it should have some curvature, but this guy is just sitting on a flat boundary, and it should not have curvature. Okay, and so then with all these, so that's a boundary corrected Euler curvature, and then you get elegant formula. So let's go to theorems. It's not time for theorems. So the theorem. So there is a discrete Gauss-Bonnet theorem. No, I think it's here as a double N. It's not Bonnet. So theorem, so this is a discrete discrete version of Gauss-Bonnet. So it's the following. That's so it's the sum over X in my so now XE could be any triangular graph. So all the faces are triangles, otherwise no regularity conditions. So it applies to my regularized point graph, no matter what the configurations were. It can be connected, disconnected, can have any singularity, certainly applies to the configurations. Doug has shown it's a perfectly fine triangular graph you can make of them. And so then if you sum this new curvature, so you get 6 times the Euler characteristics plus 3 times something interesting, namely the perimeter minus the number of boundary particles. So this here is just the Euler characteristic, and the second term is a little more subtle because it's 2 versions of boundary, but it's the difference between them which appears. But okay, and so this was done by Knill for nice configurations, and me and Lucia De Luca, so my co-worker in 2018, general configurations and the error term. So we figured out this error term. So it has a nice formula in terms of this perimeter, which I defined, and the number of boundary particles. So that's the first result. So maybe let's also and the Euler characteristic is just the alternating sum of the number of okay, so what is chi of X is basically V0 minus V1 plus V2. So this is number of vertices in X, number of edges in X. This is the number of faces in X. And so here, for the Euler characteristic, it will be the same whether or not I have triangulated. So that's the same for the triangulated. So that's just the Euler characteristic. So maybe let me maybe actually um, um, yeah, so let's see how much time would I have. So
5 minutes.
5 minutes, okay. Um, So I think I want to, okay, maybe I don't do proofs, but rather keep stating results. So I want to finish the decomposition and then maybe we can do the proofs tomorrow. So the next theorem is then the decomposition of the number of edges. So, and I write it because in the energy, this appears with a minus sign. So it's minus the number of edges. It's basically minus 3 times the number of particles plus the perimeter plus the defect measure plus 3 times the Euler characteristic. So, so that is a nice decomposition because so that's the edges of the original graph, and so basically this term is gone. So this wants a nice shape. This wants no defects. And in fact, so the Euler characteristic in the plane, it counts the number of connected components. So this is here the number of connected components, and so it wants connected sets. So somebody asked me earlier, why did I not like this old proof by Heitmann and Radian? Well, I didn't say I didn't like it, but it was not so transparent. But with this decomposition, it's already nice. You have different contributions in the energy, and whenever we see different contributions in an energy, we ask ourselves, what are these contributions doing? So they want to do something. And so now, so that's this decomposition. And so in particular for connected sets, this guy drops and this guy drops. So then we only have to play between 2 terms, which is the perimeter and the defect measure, which is a hell of a lot easier than playing with 4 terms or with the featureless energy. And so then I finally want to come to the decomposition of the whole energy. So that's now very simple. And so so another theorem, so decomposition of the energy of X is, so this is basically the sum 1 less or equal I less than J. So yeah, so does that look? So we have the V of X minus J. So we have the decomposition of the whole energy, and so then so let's say how do I do it this way? So I think the best. Okay, so so it's basically the following. So now P of X is equal to so minus 3n plus P of X plus U of X plus 3 times the Euler characteristic of X plus elastic energy plus the non-bonded interactions. So if you have something long range, as Doug was having, then one has to worry about this term. If it's short range, one doesn't have to worry so much about this term. And so how are these defined? So the elastic energy is simply it's the following. So it's so a half the sum over x, y in x. And sorry, and the x minus y is in the bond interval. So let me draw my bond interval again. So so the AB, so the theta sits here. So it's the guys sitting sort of here. So for these, I just take the true energy they have, V of x minus y bar minus V min. So and this was in our case normalized to -1. Okay, so this was normalized to -1. If it's not normalized to -1, we take out the V min. So it's just the deviation within a bond from the minimum. So that gives you the elastic energy of that bond. Okay, and so now the non-bonded interactions, they are done in an obvious way. So it's again with a half to avoid double counting. So then it's the x, y, and x, and so x minus y not in a alpha beta. So then okay, and so now these non-bonded interactions, you find them really in the physics literature everywhere. So for example, in molecular molecular dynamics packages. So for example, CHARM is the chemistry at Harvard package by Martin Karplus. So you definitely split in physical literature on the molecular dynamics, you always split off the non-bonded interactions. Okay, and so that we've done here. And so now the non-bonded are more tricky. So if they are somehow dominant, we have to think about it. So yeah, for me, it's a challenging thing to think about these non-bonded ones. Maybe one can renormalize and make them short range by some tricks. Like for the Coulomb, in the work of Codina and Milchair, always there's some screened Coulomb, which is shorter range, yeah, by subtracting some uniform background and stuff like this. So it might be that one can, by screening or other tricks, one can turn long range into short range. But the elastic energy, I can also tell you what it wants. So the elastic energy, it just turns topological crystallization into geometric crystallization. So it wants geometric rigidity, because this wants all bonds to equal to 1. And so if you have a sort of flabby sheet which is a perfectly fine triangular lattice, but the bond lengths are not 1, it just makes it rigid. Yeah. So it really so this term, so we can also say what it wants. Rigidifies stretched or compressed bonds into unit lengths bonds, and sort of then that gives you some global rigidity. So I guess yeah, that's the sort of decompositions I wanted to explain, and then so the message is somehow with the right definition of the defect measure, the perimeter, and so on, one gets a nice decomposition of the energy into well-defined contributions, which all want to do a well-defined different thing. Okay, and so I think this is really again in this picture that you do not have when you write this featureless double sum over particles of all the interaction terms. And so yeah, here we go. Thanks for your attention, and we continue. Yeah, I guess tomorrow. Thank you.